Hello, we are group number 6 and we chose to optimize a heat exchanger. Welcome, my name is Charles, I'm Kyle, and I'm Shantanu. For our project we decided to do a heat transfer problem. Our model consists of a tightly wound nichrome wire coil that supplies a 10 amp load to a car battery. Since there is resistance in the wire, the coil will begin to heat up. To stop the wire from getting too hot, it will be cooled by convection through the use of a fan. We decided to do a multi-objective optimization problem. Our objectives are to minimize the pressure drop through the coil and to also minimize the temperature at the end of the coil. We decided it would be best to model our wire coil as a hollow cylinder. It was also necessary to use a differential element so we could calculate the temperature change throughout the coil. There were also a few assumptions we made to avoid the problem from becoming too complicated and thus computationally expensive. We assumed that there is uniform heat flux throughout the wire. We assumed that the system has reached steady state so we can ignore transients. We also assumed that the thermophysical properties of air and the cylindrical coil are constant. Lastly, we assumed that the primary method of heat transfer is forced convection. Here is the problem derivation for the air temperature. This is a lot to take in, so please pause and make sure you understand before moving on. The main takeaway is that the temperature of the air can be obtained from equation 13, boxed in red. This ultimately allows for the calculation of wire temperature. Another parameter we explored in this project is pressure drop. The pressure drop is dependent upon a friction factor F. The equation used to calculate the friction factor will depend on the flow conditions of the air as it interacts with the coil. The friction factor value is then used in the equation boxed in red to calculate the pressure drop. Originally, our objective was to minimize the volume of the coil, and our design variables were length of the coil and mass flow rate. The figures below are our original response surfaces. Unfortunately, this model presented no trade-off. From looking at the response surfaces, it is obvious that the optimal solution is a smallest possible coil length with the highest possible mass flow rate. To alleviate this issue, we added the pressure drop and we made the diameter a design variable instead of length. These two figures are the response surfaces that we obtained once we switched to a multi-objective optimization problem. The only constraint that we put on this new system was that the Reynolds number must be less than 5 times 10 to the 6th. We were relieved to discover that now there is an interesting optimization problem. The pressure drop is minimized at a large diameter and a low mass flow rate, whereas the temperature at the end of the wire is minimized with a small diameter and a large mass flow rate. Based on this, our Pareto frontier is expected to be a curve that goes from the top left corner to the bottom right corner. The optimization method that we chose to use for our problem was the epsilon constraint method. Although we could have used something like the weighted sum method, the epsilon constraint method is more reliable, so we felt that was a better option. Also, we epsilon constrained the pressure drop. As I mentioned previously, the Pareto frontier behaved as expected. It goes from the top left corner to the bottom right corner. Based on these results, you can have a coil that will heat up more and have a small pressure drop, a coil that stays cooler and has a large pressure drop, or choose something more in the middle. One thing that is important to note though is that once the pressure drop starts to get low, the temperature begins to rise rapidly. The most important thing that we learned from doing this optimization study is that having a small diameter and a large flow rate will keep the wire at a lower temperature, but the pressure drop will become very large. Conversely, if we have a large diameter and a small mass flow rate, the temperature will be higher and the pressure drop will be very low. One interesting thing to note though is that the temperature at the end of the wire only varies a small amount compared to the pressure drop.